The Millikan oil drop experiment. The charge of an electron was first measured by the American physicist Robert Millikan during 1909-1930. In his experiment, oil was sprayed in very fine drops about 10 to minus 4 millimeters in diameter into the space between two parallel horizontal plates separated by a distance d. A potential difference VAB was maintained between the plates, causing a downward electric field between them. Some of the oil drops acquired a negative charge because of frictional effects or because of ionization of the surrounding air by X-rays or radioactivity. The drops were observed through a microscope. Part A. Show that an oil drop of radius r at rest between the plates remained at rest if the magnitude of its charge was q is equal to 4 pi over 3 rho r cubed gd over VAB, where rho is oil's density. Ignore the buoyant force of the air by adjusting VAB to keep a given drop at rest. Millikan determined the charge on that drop provided its radius r was null. Okay, so by adjusting VAB, he made sure that the oil droplet was at rest and determined the charge on that droplet. Okay, so let's show that this is the charge. Now, first of all, we're going to neglect the buoyant force. So let's note that here. We will neglect the buoyant force. Now we have these two parallel plates, plate A and plate B. There's a potential difference, VA with respect to B, VAB. So here's the oil droplet. The oil droplet is under the influence of the gravitational force Fg pointing down. Because the electric field is pointing down, the electric force it will feel for it to remain at rest has to be pointing up. As you can see here, and d is the distance between the two parallel plates. The volume of the droplet is 4/3, assuming that it's a perfect sphere, 4/3 pi r cube. The gravitational force it feels is its weight, mg, which is its density multiplied by its volume multiplied by g. So because the volume is 4/3 pi r cube, we will have here as the gravitational force 4/3 pi rho g r cube. The electric force it feels, it's the charge on the droplet multiplied by the electric field in magnitude Q times the electric field E. The potential of A with respect to B, VA minus VB, is minus the path integral from B to A, electric field dot product with displacement dr. And this is basically the path integral. So we find that VAB, potential of A with respect to B, is minus the integral as y goes from 0 to d, because this is my y-axis I have defined here, and B is at the y is equal to 0 plane. So electric field points in minus j hat direction, E in minus j hat. The displacement is in plus j hat direction, dy j hat. So I find that potential of A with respect to B is E times d. Why? Because this integral will give me y as the result, and y evaluated between 0 and d will be d. The minus signs will cancel. So I find that instead of the electric field E here, I can write the potential difference VAB divided by the separation between the plates D. All right. So the electric force the droplet will feel, FEL, is the charge Q multiplied by the potential difference, VAB divided by D. VAB divided by D is the electric field magnitude. So at equilibrium, the charged droplet will remain at rest. That means the net force on the y-axis should be equal to 0. The electric force should be balancing the gravitational force. So the electrical force I have here is Q VAB potential difference divided by the separation between the plates. The gravitational force, on the other hand, is its volume 4/3 pi r cube multiplied by density, giving me the mass, multiplied by gravitational acceleration. So if I solve for Q here, I will find that Q, the charge on the droplet, is 4 pi over 3 rho r cube g, and it will be multiplied by d because I will take it to the right hand side. So it will be rho r cube g d, r is the radius of the droplet, divided by the potential difference VAB. So this is my conclusion about the charge this droplet should have. So let's compare it with the answer I was supposed to get. Rho r cube gd divided by VAB times 4 pi over 3. So that is the correct answer. Now part B. Millikan's oil drops were much too small to measure their radii directly. Instead, Millikan determined R by cutting off the electric field and measuring the terminal speed Vt of the drop as it fell. The viscous force F on a sphere of radius r moving at speed v through a fluid with viscosity eta is given by Stokes' law. F is equal to 6 pi eta rv. When a drop fell at the terminal speed Vt, the viscous force just balanced the drop's weight mg. Show that the magnitude of the charge on the drop was Q equals 18 pi d over VAB square root of eta cube Vt cube divided by 2 rho g. Okay, now I have F, the viscous force acting on the drop. So F is the viscous force, and it is given by Stokes' law, 6 pi eta radius times the terminal speed when I reach the terminal speed. The net force on the y-axis will be 0 because if I reach the terminal speed, the acceleration should be 0. That means this viscous force should be balancing the weight. So I will find that the viscous force 6 pi eta rv terminal should be equal to the gravitational force, which is 4/3 pi r cube rho g. Now you can see here that these pi's will cancel, and I will have one of the r's disappearing as well, so this will become r squared. Okay, so let's rewrite this result here. R squared is equal to so you can see I will have 3 times 6, 18 divided by 4. So I will have R squared is equal to 18 eta V terminal. So that is the left-hand side, 18 eta V terminal divided by 4 rho G. So here I will have 4 rho G. Now this is going to become 2, this will become 9, and I will see that the radius is given by r is equal to on the top I have 9 eta v terminal. At the bottom I have 2 rho g. Then this is going to be inside the square root. All right. So if I go back to my result for the charge, then I'm going to write Q is equal to 4 pi over 3 rho g d divided by VAB. So I'm copying this result from part A, 4 pi over 3 rho g d over VAB. Then I have r cube. For r cube, I will have 9 eta viscosity terminal speed Vt divided by 2 rho g to the power 3 over 2, because r is this expression to the power 1/2. So then I have to the power 3 over 2 for r cube. So let's put everything inside this square root and see what happens. So this will imply that q is equal to, so 4 pi over 3 inside the square root will become 16 pi squared over 9. That's the first term. Rho gd over VAB will become rho square g square d square, rho square g square d square divided by VAB square. Then I have the cube of r, so 9 cube eta cube v terminal cube divided by 2 cube, which is 8 rho cube g cube, and all of this to the power 1/2. So that's all inside the square root. Now let's see what happens. This 9 will make this 9 cube 9 square. This 16 will become 4 if I divide it by 4. If I divide 8 by 4, I will obtain 2. And then I will have one of, so this rho cube will become, because of this rho square, it will become rho, and then I will have here this is becoming g square, and here I have g cube. So this g square will get rid of this g cube and make it g. All right. So I was just confused. This is 9, but this is g. All right. So let's make sure that this is not getting confused. This is g, that is 9. So q will become square root of 4 comes out as 2. Square root of 9 squared comes out as 9. So I will have 9 times 2. Pi squared comes out of the square root as pi. D squared over VAB squared comes out as the square root as D over VAB. And then inside the square root, what remains? I have the viscosity eta cube. I have V terminal cube. And then I have a 2 rho g remaining inside of the square root. So I can write my final answer. If I multiply 9 by 2, then I can write Q as 18 pi d over VAB, the potential difference. Then I have eta cube V terminal cube divided by 2 rho g, all inside the square root. Eta cube V terminal cube over 2 rho g inside the square root. So let's compare the answer I have obtained with the suggested answer from part B, 18 pi d over VAB square root eta cube V terminal cube over 2 rho g. So that matches the suggested answer. Okay, so we're talking about Millikan's oil drop experiment. In this experiment, we're trying to determine the charge of an electron. The oil is sprayed in very fine drops into the space between two parallel plates kept at a potential difference VAB, plate separation D, with a downward electric field. Some of the oil drops acquire a negative charge because of frictional effects. So this negative charge results in an electric force that is pointing upward towards plate A, and it also feels a gravitational force Fg pointing down. We neglect the buoyant force inside the fluids or in air here. So we're going to have these two forces balancing each other. The electric force is Q times E. The gravitational force is mg, which is density times volume times g. And for the electric field, since the potential difference VAB is minus the path integral from the starting point to the end point, dot product of electric field with displacement, we find that electric field is the potential difference VAB divided by plate separation D. If we substitute this for E in the electrical force, and note that at equilibrium we have a zero net force, electric force is balancing the gravitational force, we obtain the charge. In part B, we turn off the electric field, and because of the viscous force here, you can see because the radii are too small to measure, we cut off the electric field and measure the terminal speed of the drop as it fell. The viscous force on a sphere of radius r moving at speed v through a fluid with viscosity eta is given by Stokes' law, and when it reaches the terminal speed, the net acceleration is 0, therefore the net force on the y-axis is 0. So this viscous force balances the gravitational force, which gives us an answer for the radius in terms of viscosity, terminal speed, rho, and g. If we substitute that into our expression in part A, we obtain the charge given in terms of eta v terminal rho g, the separation between the plates, and the potential difference. Now, this viscous force is proportional to r, as you can see here. On the other hand, we have the gravitational force is proportional to r cube. So we had the requirement that the buoyant force is to be neglected in part A. So we have the same assumption here as well. The buoyant force is neglected. But if this is inside a fluid with basically viscosity eta, we can include this viscous force as being proportional to r, and if we get rid of the electric field, this viscous force is going to be the dominant factor. So basically, if you have the same setup here in part A, the electric force is to be much greater than the viscous force so that it can be neglected in this calculation. But here, because we got rid of the electric field, the viscous force is the only force that remains, and therefore it's going to be determining the terminal speed of the oil droplet.